Is my screen visible?
No, now it's not. It was, but
Oh, just a second. Window, share. Yeah, is it visible now?
yeah.
All right. Yeah, hi guys, welcome to your second KTS session. Today we'll be talking about naive Bayes, KNNs, and SVMs. I'll be talking about SVM. I'll be talking about KNNs and naive Bayes, and Vedant will be talking about SVMs. So yeah, KNNs or K nearest neighbors, we'll start talking about that. So this is based on the topic of birds of a feather flock together, basically. So in KNNs, when you it's used for both classification and regression, and the way you determine the class or the value of a data point is via its neighbors. So it just finds the k closest data points and it asks those data points to vote to figure out the class of a new data point or to average and figure out the value of a nearest data point. Uh, it is solely based on your neighbors. There is no other algorithm or training phase here. So yeah. So how it works? You first find the k nearest neighbors to a new. So you have a data set. You put a new point in it for which you want to find its class or you want to find its value. Let's talk about classes first. So if you want to define you want to see which class a data point belongs to in a data set, you place that point in the data set and you calculate the k nearest neighbors of that point via some distance metric. So we'll talk about those distance metrics later on. So via some distance metric, you calculate the k nearest points to that data set uh, in that space. And then once you have those k nearest data points, you ask those k nearest data points to vote. It's like a voting system. So for example, I choose k as 21. And my point around my point, the 21 closest points have 15 of class 1 and 6 of class 2. So that means the 15 will overpower 6 in voting, obviously. So my data point is of class 1. So the majority class is assigned to your new data point. Yeah, so training step. KNNs don't really have a training step. All you do is it just memorizes your training data set, and then you place a new point, and it does its whole algorithm. So you choose a value of k, you choose a distance metric, it stores it stores or memorizes your training data points, and then it does its nearest neighbors thing and identifies the class of the point. So this is an animation. So if you have a new data point here, you can see how it's calculating the distance, and once you have a value of k, it chooses uh, the class. It lets them vote. So in this case, we chose k to be 1, 2, 3, 4, 5, and amongst its 5 nearest neighbors, 4 of them were from the blue class, and 1 was from the red class. So by majority, this point is now in the blue class. So yeah, as I said, there's no training in KNNs. It's only comparing values. That's why it's also called a lazy algorithm. It doesn't try to memorize. It doesn't try to learn any pattern from the training data. It just memorizes the training data and then it puts a new point in that space with the training data in it, and it compares its distances, asks them to vote, and then assigns a new class. It depends all on how you define the closeness and how you choose the value of k. These are the key parameters in this algorithm. One is k. These are the number of neighbors you want to consider. So how many neighbors surrounding your data point should take part in your voting system to define what class your point belongs to. Then you've got distance metric. You've got multiple distance metrics such as Euclidean, Manhattan, Minkowski, Chebyshev, Hamming distance, and so on. We'll talk about them later on. And a weight function. Now you can also define if each data point has an equal weight or if closer data points have more weight, further data points have less weight, and so on. So yeah, choosing the right value of k. Now choosing the right value of k is very important because that can play a huge role in defining what your data point is, right? If your k is too small, then it will overfit. It'll overfit because say I choose k as 1. That means my nearest point defines who I am. Now that obviously is can overfit like a lot because say your nearest point is actually noise but not a real value, then your new class will be the same class as your noise, so it overfits. Similarly, if k is too large, that means you're asking it to consider a huge number of neighbors. Now, How that is bad is because if a value of k is so large that you step into your other class's territory, your other class will start influencing your decision as well. So it is very important to choose the right value of k. How do we choose this right value of k? We have multiple methods. We use cross validation mostly, where you can run an algorithm where it tries on multiple different values of k from a start to an end. You can plot accuracy or error versus k values, and you can choose the k with the best score. All of these methods are a little slow, though. We'll talk about why later on. And also, one more thing is you have to try to stick to odd values of k, because it is especially in terms of binary classification. Because if you have, say, two classes and you choose an even value of k, there can be ties, and in that case, you won't be able to assign a class to it. And avoid overfitting to the validation set. And after a point, if you increase the k to a very high value, you're just blurring the model, because it's not having a very strong, you could say, decision on choosing the right class for that point. So yeah, this is an animation again. So you're trying different values of k here, and you can see how the error changes for different values of k. So I think in this case, when it was k is equal to 3, we had the lowest error. Yeah. Yeah. So this is we'll talk about some distance metrics now. The first one is Euclidean distance, where it is like the most common distance metric. It works well on all when features are continuous as well. And it's this formula right here, which is xi minus yi whole squared summations with the under root in it. Then you've got Manhattan distance, which is this, and Minkowski distance, which is this. By the way, these two distance metrics are derived from this. If you put p is equal to 2, you'll get Euclidean distance. If you put p is equal to 1, you'll get Manhattan distance. And when do you use Manhattan versus Euclidean? So if you have higher dimensions, you generally choose Manhattan distance, because what Manhattan distance does is it finds the distance for every axis. So if it's three-dimensional data, it will find the distance along x-axis, y-axis, and z-axis. But if I have Euclidean distance as my, it just finds the diagonal distance to the point. It just finds a straight line distance to that point. So an issue with Euclidean distances, as your dimensions increase, Euclidean distance tends to start failing because of something called curse of dimensionality, where what happens is if your dimensions increase, the distance of 2 points from a reference point, the difference of the distance of 2 points from the reference point starts to fade away as your dimensions increase, which could then hurt your model. You've also got Hamming distance. Hamming distance is for categorical or binary features, and it is used when data is non-numeric. So Hamming distance is basically like a score. Say if I have to compare two words, um, choosing and chosen. So choosing and chosen, then what Hamming distance does is it goes over. Oh, wait, so I'm so sorry. You can't use choosing versus chosen. Say you have just two words like A, B, C, D and A, C, D, E. So what Hamming distance does is it's used for same length strings, and it goes one by one over the string and it compares the values. So the first letter of A, B, C, D and A, C, D, B were the same, so it gives a score of 0. If you find something where your letters do not correspond, then it gives a score of 1. And you add this together to find the distance. Yeah, regression using KNNs. Yeah, as I said, so KNNs using classification was where you choose a k nearest neighbors, and the k nearest neighbors get to vote to choose what class you belong to. In regression, you choose a k nearest neighbors, but the value of your data point is defined by the average of all of the data points in your k nearest neighbors. Yeah, that's about regression. So pros and cons of KNN. So pros, it's very simple, right? It's easy to understand and implement. It's a simple formula. You use a distance metric, you find the nearest neighbors, you vote or you average, and you find the value or the class. There's no assumptions you make, and it's very simple. There's no training phase, right? You fit the training set, and then on top of that, you put a new point in that same space, and then you calculate your distances. Now, this is where the cons also come in, because you're calculating. So if you have a very large data set, for every data point you want to classify or perform regression on, you have to compute the distances of that point with respect to every other data point. So if I have 1,000 data points in my training set and I want to find the class or the value of my 1001st data point, then I have to compare the distances of that point with respect to all the 1,000 data points in my data set. So you can see how it becomes computationally expensive because of that. So that's where I said key, if you want to compare different values of k, it tends to become a slow process, because for every time you have to make a plot of k versus error, you have to compute that point with respect to all its other data points for all its different values of k. So it ends up becoming slow, it ends up becoming memory intensive. And yeah, I already talked about Koshal dimensionality. So yeah, putting it all together, this is a very simple algorithm. You first calculate the distance via distance metrics, Euclidean, Manhattan, Minkowski. There are multiple more. You identify your nearest neighbors. Via a k value, you aggregate them, and then depending on classification or regression, you either predict the class via voting, or you do regression where you predict the value via averaging. Yeah, then code implementation. I'll just open that. Yeah, right here. So this is a simple code implementation for KNNs. It's a simple module, and we're using the iris dataset to classify a data point based on its surrounding data point. So the iris dataset has three flowers in it, and I'll just show the dataset to you guys. Yes. So the iris dataset has all these features about the class, and then it has three species of the flower, and based on these, we try to figure out what the species is. So we load all the modules. I'm so sorry, we're not using Iris. I was confused. So I actually switched to MNIST. I'm really sorry. So MNIST is a handwritten data set where you've got handwritten numbers from 0 to I think 9 or 10, and each pixel value. Sorry, so you have a lot of pixel values are given, and you have to figure out what number it is. So we're using KNNs for that. So I've just tried out different neighbors here: neighbors 5, neighbors 3, neighbors 15, and it's a simple algorithm which is k neighbors classifier. You choose a number of neighbors, you fit it, you predict it, and then you find the accuracy. So I just tried it for three different values. You can we can obviously plot a graph for different Ks, and I think here we see that 3 performed the best out of all of them. Yeah, this is the confusion matrix. I just plotted it for the number of neighbors 5, and yes, so it's from 0 to 9. Yeah, and that's K nearest neighbors. Now I think Vedant can continue with the next thing.
Okay, one second. I'll share my screen. Can you see the presentation?
Yeah, before that, if anyone has doubts, you can ask them. Yeah, I think you guys can continue.
Anway, your mic is okay. So now we'll do SVMs. So support vector machines, it's again a linear classifier, but with a twist. So support vector machines, they try to find the best linear boundary between two clusters. So for example, if you look at this, there are many ways to separate this data. So this is one, this is one, this is one. There's probably infinite more, but only one of them will be like the best one, which in this case, as you can probably guess, it's this middle one, because we're leaving the most space between the data here. In this line, because we're doing too close to the yellow point, technically we're classifying this point as red, but then because it's so close to this yellow cluster, there's a chance that it's actually just belongs to the yellow class. So just creating a linear separator is not enough. We want to create one that leaves the widest margin between the two clusters. And that's basically what SVMs does. It does this with the help of points called support vectors. So what an SVM classifier would look, it would look like this. It has these margin boundaries, and that basically helps us find the decision boundary. The margin boundaries pass through some data points, which are called support vectors. So in this case, you can see we have 3 support vectors, 2 yellow ones and 1 red one. And then these 2 lines are parallel. Midway through these lines, you have the decision boundary. We define the margin as the distance between these 2 margin boundaries. And the goal of the support vector machine is to maximize this, because as we just said, in this case, this line is the best classifier because it leaves the most space between the data points. So it leads to better generalization. So that's the goal of support vectors, to leave the largest margin. So SVM aims to find the boundary that is as far away as possible from the nearest points. This distance is called the margin. So now whatever we do, the main goal will be to find what this margin is in terms of how we define the model, and then to maximize that margin. So before we go to that, we look at what a hyperplane is. A hyperplane is just our decision boundary. In 2D, it's just a line. In 3D, it's a plane, and then so on. We call it a hyperplane beyond that. The equation is given by Wx plus b, where x is your input vector. So in 2D, x will be 2-dimensional. W will also be 2-dimensional. You take the dot product of this, and then you add a bias, which gives you some value. So in 2D, for example, you'd have 2 points defining your input, say x and y. Your W would be, say, W1 and W2. Your hyperplane equation would become W transpose x, which is the same as W dot x plus v, which gives us this, which of course is the familiar equation of a line. So we need to know what a hyperplane is, because that's basically what we're trying to find in SVMs. So now that we know what a hyperplane is, we'll go into the math. But before that, I'm going to call this thing Wx plus b. I'm going to call it the score of x, so that you don't have to listen to me say the same thing again and again for the next few slides. So just remember that if I say score of x, it basically means Wx plus b, where this is the dot product. So going to the math, we'll first set the scene. So we have the training data. Xi is the input and yi is the target. The target, in this case, we're doing binary classification. So we'll have 2 possible values, either +1 or -1. The green labels are +1, the red labels are -1. Our goal is to find this decision boundary, again, to maximize this margin. In this case, we can see once we find this optimal decision boundary, we have 3 support vectors. 2 of them are red and 1 is green. So we can also, the regions of space are defined in terms of the equation of this decision boundary. Any point that lies on this line satisfies this equation. So Wx is equal to 0, or basically score is 0. Any point that lies on this line satisfies the score is 1, but here score is -1. These orange lines where the score is plus or -1, we call them the margin boundary. Midway through this, we have the decision boundary. Any point that's to the right of this, so in this green region, the score will be greater than 1. And any point that's to the left of this margin boundary, the score will be less than -1. This is important because we'll be using this a lot. So on the decision boundary, we have score 0. On these 2 margin boundaries, we have score plus or -1. Over here, the score is greater than 1, and over here, it's less than 1. So now we just combine these 2 graphs, and you get this. So this is your training data. The goal is to find this classifier. These 3 are your support vectors. Over here, for all these points, the score is greater than 1. Here, the score is 1. Here, the score is 0. Here, it's -1. And here, it's less than -1. This is our separating hyperplane, with W and B being the parameters which we want to find. So now that we've defined the model, we need some way to find the margin. By the way, in this case, because W is normal to the decision boundary, this W cap is perpendicular to our boundary. So now that we've defined the whole scene, we need to find an expression for the margin in terms of W and B, because that's what we're trying to optimize. We're trying to maximize the margin. So let's say we take any point on the decision boundary. We're at some point X, which is located on the decision boundary. Naturally, for that point, we have Wx plus b is equal to 0. Now, if I go from this point on the decision boundary to the parallel point on the margin boundary, this distance that I cover will be equal to half of the margin, because the decision boundary is midway between the 2 margin boundaries. So if I go, let's say some K units here, the margin will be 2 times that K. This distance, sorry, this thing that I travel from the distance boundary to margin boundary, it will have to be in a direction perpendicular to both these lines. And that direction is given by W cap. So initially I'm at X, which is on the decision boundary. So it satisfies score equal to 0. Then I go K units along W and I reach the margin boundary. Now, because this is on the margin boundary, this equation, sorry, the new point, which is X plus KW, that should satisfy the equation for the margin boundary, which is W dot of X plus KW cap plus B is equal to 1. So again, just initially I was at X, which is on the decision boundary. Then we went K units along W towards the margin boundary, and we reached here. The goal is to find K, because from this we can see that K is simply half of the margin. So initially X is on the decision boundary. Finally, we reach here. If we just open this and open the brackets, we get Wx plus this. This is the unit vector of W. We just swap these two terms. So then this part, Wx plus B, is anyways equal to 0 because, as we said, X is on the decision boundary. So then we get K norm of W is equal to 1. So K is equal to 1 over norm of W. So we wanted to find the margin size. Just finding K was enough for that, because again, K is half of the margin. So margin will be equal to 2K, which is 2 over omega. So finally, the goal, which was to maximize the margin, if we want to maximize this term 2 over norm of W, because 2 is anyways constant, it will be the same as minimizing the norm of W. So now our goal is clear. We want to minimize this norm of W, which is the vector that is perpendicular to our decision boundary. And for the sake of mathematical convenience, we, instead of optimizing or minimizing norm of W, we minimize this. They're both the same, but when we take the gradients and all, it becomes easier. So just to summarize, we wanted an expression for the margin because that's what we're trying to maximize. We did all this stuff and we finally got that margin is 2 over norm of W. We want to maximize the margin, which is the same as minimizing W. And so, which for convenience, we try to minimize half norm of W squared. Now, this is not good enough on its own, because if I told you to just minimize this expression, you'd say norm is always positive. So this will become 0. But obviously we can't put this as 0. Otherwise, then the margin will tend to infinity. And that doesn't make sense. So we're trying to get the widest margin, but we have to apply some constraint on this minimization. The constraint that we apply will be in terms of the classification. Again, remember here, for the green points, the score was either greater than 1 or 1 for the support vector. For the red points, the score was either -1 or less than -1. So for all green points, the score is greater than or equal to 1. For all red points, the score is less than or equal to 1. The constraint that we're applying is if yi is 1, that is, if it is a green point, we want the score to be greater than or equal to 1. And if yi is -1, we want the score to be less than or equal to -1. Basically, we're saying we want the model to classify every single point correctly. So you try to minimize W, but you make sure that all the points are classified correctly, so that obviously that's the goal. So we have two constraints here, but we can simplify or join these two expressions by just taking a product. We take yi times this, because -1 into -1 becomes plus. So we get, finally, this is our constraint, that yi into the score of all points should be greater than 1. So finally, our goal is to minimize half of the norm of W square, given this constraint that yi times the score should be greater than 1. This is basically saying you have to get the biggest margin that you can. And this is saying that you have to classify all the points correctly. So get the widest margin such that all data points are classified correctly. This is our optimization task that will help us find the SVM classifier. This form is called the primal. Now, while it looks okay, we don't want this form. We want to simplify this, mainly because we want to remove W and B. And one more thing we'll see later when we get that form. But first, just understand how we got the primal, because we'll just build on this after this. So just repeating, we wanted to find the margin, how wide it is. We did all this stuff and we got margin is 2 over norm of W. We want to maximize the margin or basically minimize the norm of W, but we can't just blindly do it. we have to apply some sort of constraint. The constraint comes here where we're basically saying we want to classify all the points correctly. So this becomes our constraint. And finally, we minimize this such that you satisfy this. So this is your primal. Now we have a constraint and we want to optimize. This is an example of Lagrange's constraint optimization. So for those of you familiar, it's basically what you want to minimize or maximize minus alpha times your constraint. We take this to the left side. So we get our g of x function. So this becomes our Lagrangian, and this is what we want to optimize now. Because we want to optimize it, in this we can only change w and b because obviously xi, yi are fixed, and alpha I just alpha I are the Lagrangian multipliers, so we don't bother that just now. So because we want to find the extremum point of this, we differentiate it with respect to first the vector w. If we differentiate this, the first term just becomes w. The second term, it's alpha I, yi, w dot of xi. We're differentiating it with respect to w, so this w just goes off, and we get w minus sigma of alpha I, yi, xi is equal to 0. Take this to the other side, you finally get the vector w is the sum of alpha I, yi, xi. Now, in some support vectors, support vector machines, this algorithm, the classifier that we finally get, it only depends on the support vectors. It doesn't depend on any other point. One sec. Yeah. So over here, the support vectors the classifier only depends on the support vectors. If I remove, let's say, this green point or this point, it doesn't change our classifier. That remains the same. It only depends on these support vectors. So W, which is the classifier, it should only depend on these support vectors, not on any of these points. That is the non-support vector points. So here what we got was W is a sum of all the training data points. But we also know that W should not get affected by the non-support vector points. So alpha I for those points will have to be 0, because if it's not 0, then we're basically saying for some change in the non-support vector points, our decision boundary also gets changed, which is not the case. It only depends on the support vectors. So for the support vectors, your alpha I will not be 0, but for all the non-support vectors, alpha I has to be 0. This is actually one of the main benefits of doing this whole thing and not just stopping at the primal. So we took the derivative with respect to W. We got this thing. We can again take the derivative with respect to B. We'll get this anyways 0. This becomes, first term becomes 0. The second term will become sigma alpha y, and this again becomes 0. So this is our second equation. So now we have three things. First, we had our initial Lagrangian. Then we got an expression for W. In this case, note that alpha I for all the non-support vectors is 0, because the non-support vectors doesn't contribute to the decision boundary. And third, we got this. So now our goal, again, as we said in the beginning, the goal is to remove W and B from this equation. If it depends only on alpha I, then that would be ideal. So what we do is we put this expression into the first one. So we'll put that over here. So for the first W, I'll be using the subscript I. For the next one, I'll be using subscript J, just to make things clear. So this will become half of sigma alpha y xi into sigma alpha j yj xj. This is simply W dot of W. For this one, we can again use the subscript J because I is already here. So we'll get sigma alpha I y xi into alpha j yj xj minus we get this term plus sigma alpha. Now note over here, because B is a constant, we can pull it out of the summation. So this becomes B times sigma alpha yi, which we already know that alpha yi is 0. So this entire term becomes 0. And here, if you see, these two terms are basically the same. Because here you have sigma alpha yxi into alpha j yxi, and you have the same thing here. It's just that here you have half of that, here you have minus 1 of that. So we can simplify this expression. We'll get sigma alpha I minus half of this, because it's half minus 1. So we did all this. So now our goal becomes to maximize this L over all alphas. Our new constraint being, first of all, the Lagrangian multipliers have to be positive, greater than or equal to 0. And second, this constraint that we got from this equation. So just again to tell you what we did. We got this part. I hope this is clear how we got the primal, but we don't want our optimization to have this W and B. And there are some things that are not ideal about this, which I'll discuss later. Basically, we don't like this form. We want to simplify this further. So we took the Lagrangian, and this is the Lagrangian's form. We took the partial derivative with respect to W and we put it to 0, which gave us this form of W, which is alpha y xi. We also said that for all non-support vectors, alpha I has to be 0 because they don't contribute to the decision boundary. So this alpha I will only be non-zero for the support vectors. And secondly, when we took the derivative with respect to B, we got sigma alpha y is equal to 0. Now we have three conditions. We want L to be independent of W and B. So we use these two equations in this expression to remove W and B. Doing some sort of algebra, we finally came up with this. This thing is called the dual. It's again an optimization task, but now we're simply optimizing over all of alpha. So just a quick summary of this. We get that the primal, which is our first thing, we had to minimize half of now omega square because the margin was 2 over omega, sorry, W. Then the constraint being the class, all classifications are true. So yi times the score should be greater than 1. We simplified this to form the dual, which gave us this form. It only depended on alpha and removed W and B from the thing. Alpha I is 0 for all the non-support vectors. So why did we do this? Like, why did we have to go through all this nonsense of getting the dual part? Well, there are some properties of the dual that are nice. First of all, alpha I is 0 for the non-support vector, so that makes it sparse. It's easier to evaluate. Secondly, in the dual, if you notice, we only have a dot product with the training data. So wherever we use X, we only use a dot product. Even in the previous slide, if you see, while classifying, we do, let's say we're given some unknown point U, we only take the dot product of that and then add B to decide which class we give it. And while training also, we only use the dot product. So our entire model during training and inference, it only depends on dot products. This is something that will help us later when we see kernels, but it becomes very clear when we take the dual form. So first, it was sparse. Second, it enables the kernel trick because the data only appears as dot products. How it helps, we'll see that later. And thirdly, the duals handles constraints more cleanly. If you see the primal, our constraint is an inequality, but in the dual, our constraint is an equality. So that using quadratic programming, it becomes easier to optimize. So we finally just gotten what we wanted. Like we wanted a maximum margin, which gave us this optimization form, which basically says that while classifying all the points correctly, you have to get the biggest margin. So this is an ideal case where the data, we assumed it was all linearly separable. But there are obviously cases where the data will not be linearly separable. And it's also possible that some points, there might be outliers, which will sort of ruin our whole thing. So if you look at this case, if we set a hard margin that we want no errors, our decision boundary becomes this. But obviously it's pretty clear that this is not, this could be some sort of mistake. Wait, hello, can you hear me?
Yeah, we can hear you now.
Where did it stop, like my voice?
Just the noise part, the mistake.
Okay. So basically, yeah, we're allowing some error over here. We're allowing to misclassify one data point so that overall it will generalize better, because here it's clear that this is some noisy measurement and we don't want to give it that much importance. So far what we did in our whole optimization thing, we said that we want every single data point to be classified correctly. But this is called hard SVM, but we want to allow some misclassification so that it will generalize better. So this is called soft SVM, where you allow some sort of error into the thing. So far, we've assumed data is perfectly separable, but obviously in real life, it will not. So we need to basically relax that and allow some sort of violations allow some error in classification, but also keep a control on how much error is there. So how we do that? Before we do that, we look at the cases of error that we get, or the cases of classification. So the first case is this yellow point. It's supposed to be here and it is here. So this is classified correctly. We wouldn't want any error over here. The next one is the second case. Second case is this red point. It is located in its cluster and is beyond this margin boundary. So even this, we wouldn't expect any error for this. The third one is this point, this red point, which is clearly misclassified. And it's like it's on the other side of the other decision boundary. So we'd expect a pretty high error for this. And the fourth kind of point that we can get is this one. This one, while it is classified correctly, it is pretty close to our classifier. So we would also want to give the model some sort of penalty over here to say that, you're going too close to some points. So in the first case, there was no error. In the second case, there was no error. In the third case, we would want a high error. And in the fourth case, we would want some error. Like it should be low, but there should be some error. So we need to define a loss function which satisfies these properties. And that loss function is called the hinge loss. This is the form it takes. It looks a little complex, but it's actually pretty simple. It basically says, like, if you look in the first case, the target is +1 and the predicted value is greater than 1. So this will become 1 minus some number that's greater than 1, which this entire thing will become negative. So your loss becomes 0. Again, for the second case, it's the same. For the third case, your hinge loss will become greater than 1. For the fourth case, it will be between 0 and 1. So as we said, for the third case, we want a high error. For the fourth case, we still want some error, but it can be small. So that's why it's between 0 and 1. It's pretty easy to just verify this, so you can do that on your own. So now we've added this loss term to our overall loss function. And the goal will now be to minimize this, but we'll also minimize this loss. So initially it was just half norm of W square, which was saying we want the widest margin. But now we're adding this term. So basically for every misclassified point, this will add to the error term. And C is just a hyperparameter that controls how strictly we want to punish the model. So if C is very high, even for small errors, the overall error will increase. So a high C will try to correctly classify every point, even if we get a smaller margin. If we keep a low C value, it basically means that any misclassification doesn't really contribute that much. So it allows some violations and leads to better generalization. But obviously, a very high C would lead to overfitting. A very low C would lead to underfitting. So we need to find, again, the bias variance trade-off. We need to find the optimal value. And again, there are a lot of methods to do this, but we won't get into that right now. The main thing is we wanted to allow some sort of error. We didn't want it to do perfectly. We allowed some error, but we also wanted to keep a check on how much the error would be. We saw that there are 4 cases of classification, and we want no error in the first 2 cases, a very high error for the third, and small error for the fourth. This loss function satisfies all those 4 properties, and we simply add it to our objective function. So now this becomes what we try to minimize, and that is called soft SVM, and obviously it would lead to a better model. So this is the case where the data, if you see over here, it's still linearly separable. It has outliers, but it's still linearly separable. But there are cases, obviously, when even with a soft margin, the data is not linearly separable. Now over here, what do we do? The main idea of kernels, which is what this entire section is, kernel SVM, the main idea of that is to lift the data and make it linearly separable.
One
So for
second,
example,
Vedant.
yeah.
Yeah, we'll pause for doubts right now. Since Vedant has covered a lot, if you guys have any doubts, you can ask right now. Like regarding the derivation of the Lagrangian thing, if you guys have any doubts in that, you can ask, or any other part of SVM, if you guys have doubts, you can ask.
Should I like give a quick overview of what we've done so far? Because
Yeah,
there's lots.
just do a recap. If you guys get any doubts, you can ask. Like you can pause based on that point of time, and you can ask doubt.
Okay, fine. So we started with the training data. We have two classes in this case, green and red. Green is +1 and red is -1. I mean the target. So we define the decision boundary as wx plus b equal to 0 or score equal to 0. We call these the margin boundaries. And for them, the score was plus or -1. For this region, the score was greater than 1. For this region, the score was -1, less than -1. One doubt I had when I was doing this is why did we take score is equal to plus and -1? We could have taken some other value. And when I checked, basically the reason is if we choose some other value, then it leads to we'll finally have to scale our wx plus b part, and it just leads to some sort of optimization problems. So we take plus and -1 because that's the easiest when we try to optimize it. So these are the different regions of the space that have been defined by our hyperplane. So here score is greater than 1. Here it's less than 1. See, less than -1. Here it's equal to -1. Here it's equal to +1. So then we just combine the two and we got this thing. For all the green points, we saw that the score is either 1 greater than 1 or equal to 1 in case of the support vectors. For the red points, the score was either -1 or less than -1. It was -1 for the support vectors. One more thing, because the hyperplane is wx plus b, we know that w is normal to the hyperplane. Now, the goal of SVMs, we said in the beginning, was to maximize this margin. So we need to find some expression of the margin in terms of the model so that we can then optimize it. So how we do that is we first choose a random point on this decision boundary, and we go from this to the margin boundary. We go in a direction perpendicular to these two lines because we want the shortest distance. That is what will be our margin. So initially we were at some point x. We went k units along w cap. So our new location became x plus k w cap, and that's on the margin boundary. So it should satisfy this orange equation. So just writing that out, we get these two conditions. If we open up this expression, we get this thing. We just swap this, put this on the left, put this on the right. You get this. And because x is on the decision boundary, this entire term becomes 0. So we get k norm of w is equal to 1. So k becomes 1 over norm of w. Now k is half of the margin. So margin will become 2k, which is 2 over norm of w. So the goal, which was to maximize the margin, can now be written as minimizing norm of w. And for the sake of convenience, we instead of minimizing norm of w, we minimize this expression. It's the same thing. Now, we can't just blindly do this. We need to set some constraints. And the constraints that we set are, we want to classify all the points correctly. So if you notice here, the score is always greater than or equal to 1 when the target is 1. And the score is always less than or equal to -1 when the target is -1. So these are two constraint equations, which we can combine by just multiplying, and it becomes one simple thing. So now this is our constraint. Our final goal becomes to minimize this entire thing given this constraint. This part is basically saying you make the margin as wide as you can. This part is saying you make sure you classify all the points correctly. So get the widest margin such that all data points are classified correctly. This form of the optimization task is called the primal. Next, we have, because we don't really like this form, there are some things about this that we don't want. We try to simplify this further using constraint optimization. So we define the Lagrangian as what we want to minimize minus alpha times of the function that is our constraint. Because we have n constraints, we have an alpha corresponding to each of the constraint functions, and we get this Lagrangian. The Lagrangian depends on w and b. The other stuff is already fixed except the Lagrangian multipliers, but w and b is what we can change from our model. So we take the partial derivative of L with respect to the two of them. When we took it with respect to w, we got this expression of w. And we also said that the decision boundary doesn't depend on the non-support vectors. So for those points, it shouldn't affect our w, irrespective of what we do to the x of those points. So the alpha corresponding to the non-support vector should be 0. And the alpha corresponding to the support vectors should be non-zero. Next, we took the partial derivative with respect to b. We got this thing, and we got this equation. So now we have this one equation, this second one, and this third one. What we wanted to do in the beginning was to remove w and b from this Lagrangian, this thing that we're trying to optimize. So a simple way to do this, you just put this into this expression. You do a bunch of algebra and simplifications, and finally you get this. So now our goal becomes to maximize this function such that alpha is greater than 0 and sigma alpha y is equal to 0. Over here, if you see, there's no w, there's no b. So that's what we wanted. It only depends on alpha. This form is called the dual. So one thing to note was when you try to classify a new data point, you take the dot product with b and then you say with w and then you add b. And while training the thing that you're trying to optimize, in that also you only take the dot product. So the model only depends on dot products. This is something that we'll use later on in kernels. But for now, just keep that in mind. Okay. So we had the primal, which was this thing. We didn't really like this. We wanted a better form. So we found the Lagrangian and then we took the partial derivatives, equated to 0, and then simplified the expression, which gave us this. This you can see, the only thing that we're doing with the data points is dot product. Again, this is something we'll use later. So why did we do all this stuff to get the dual? Mainly three reasons. First, the dual gives sparsity because most of the alphas are 0 because obviously in the whole data set, you'll only have a few support vectors. So for all the other points, alpha will become 0. So this becomes easier to calculate. The dual enables the kernel trick because, again, I think I've said this too many times, but it only depends on dot products. And third, the constraint becomes easier because in the primal, the constraint is an inequality, but here it's an equality. So we can use quadratic programming and solve this optimization task pretty simply. Next, we saw if there is some sort of outlier. We don't want, if we went with our initial hard SVM algorithm, we don't want any error while classifying. So this is the decision boundary that we would get, which obviously is not ideal. We want something like this. We can misclassify one point because it might have been some error or some noisy value. So we want to allow some sort of error, but then keep that error in check. So we need to introduce some sort of loss function into what we're optimizing. We looked at the types of errors that you can get. For 1 and 2, obviously there is no error. For 3, there should be a very large error. And 4, even though it's classified correctly, because it's within the margin boundaries, it's too close to our decision boundary. So we'll give it some small penalty for that. We use the hinge loss for this. And these are the 4 cases. And you can see yourself how this will come about. So this became our new objective function. And we called C a parameter, which decides how much you want to punish the model for misclassifying. If C is large, then you're basically saying that for any error, the overall loss becomes very high. So if a high C means that you're pushing the model to classify every point correctly. A low C means that, okay, even if you misclassify, you're not being that strict with the model, which would allow you to keep a wider margin and lead to better generalization. Again, it's a trade-off. A very low C between a very high C, there's a bias variance trade-off. We need to find the optimal value. So this is the next case. Should I continue? Okay, fine. So what if the data is not linearly separable? Even with the soft margin, we saw that there was still a line that can separate the two. But there are obviously a lot of cases in real life when the data, you just can't separate it with the line. So because our SVM is a linear classifier, we can't do anything to the shape of our classifier. What we can do is we can lift or sort of move the data and project it into some other space. For example, this thing on its own, there is no straight line that can classify red and green properly. But if we project this onto some other space, then we would get something like this. So we went from a 2D space to a 3D space. And now it's pretty clear that we have this plane that can separate the red and green ones. So this trick is called the kernel trick, where you actually, no, this trick is not called kernel. This is just applying a transformation and you project it onto a higher dimensional space, which would lead to a more clear decision surface. So how do you map this into a higher space? A mapping 5x transforms our original data into a new higher dimensional thing. So for example, initially x is defined by 2 points in 2D space. We apply some transformation on x and we get onto the 5-dimensional space. So as you can see here, there would be an issue where originally we had 2 points for every data point, but now we have 5. So that could be computationally expensive in real life where, x won't depend on just 2 things. It could depend on a lot. And depending on your mapping, it could lead to an even larger amount of values. So computing these transformed vectors explicitly is very expensive because it depends on the dimension of our mapping also. And as we'll see later, there are mappings which have infinite dimensions. So obviously an infinite dimension vector is not something you would want. So finding this transformed vector slows down both training and prediction. So what we want is we want some sort of hack. And one thing that I hope you remember by now, because I think I said it too many times, is that in the dual form, sorry, the only thing we do with that data is we take dot products. So originally we had xi dot x, j. Now, once we map it to this high dimensional space, let's say we get some 5xi and 5xj. When we take the dot product of those two vectors, we'll get this. So instead of xi dot xj, we get 5xi dot 5xj. So we don't really care about the transformed vector. We just care about the dot product of the transformed vectors. So the trick is we won't need to compute this phi individually if we can just find some function that gives us this expression without having the need to go to the transformed space and all. So this function that we use is called the kernel. The kernel is basically the dot product of the two vectors in that transformed space, but you don't have to go to that space. So that's why this is called, you're implicitly lifting it, because we're not actually looking at the transform vectors. We're just assuming that, okay, if we were to transform it, this is what the dot product would become. So this gives us the power to use high dimensional spaces without even computing the transformation. So that's the kernel trick. And if we see how SVM changes with the kernels, in kernel SVM, we don't need a new algorithm because we just replace the dot products with the kernel function. Everything else remains the exact same. So if you look at our dual, initially this thing was xi dot xj, but now it just becomes kernel of xi and xj. The constraints are still the same, and the decision boundary, initially it was wx plus b, and w was sigma alpha yi xi. So we replace that xi x with k of xi x. So how that whole dot product thing that I said, how it helped is we don't need to compute the transformed vectors in the new space. We just use a function that shows what the dot product would be in that space. And we substitute that in our equations. We don't have to change anything else. So that is SVM with kernels. So there are different kernels that do different things to the data. The most popular one is polynomial and RBF. Linear is obviously just a normal case. Polynomial is used for capturing curved boundaries, and there are two parameters in this, C and T. So if you look at that, D is the degree of the polynomial. C is a constant that adjusts the influence of the higher order terms. When D equals 1, obviously this becomes a linear kernel. Higher D will capture more complex patterns, but it can overfit. So if we see this, here we have, wait, I think it's given. Yeah, basically we keep here D is 2, here D is 5, and here this is the linear kernel where D is 1. So you can see here we're just fitting a line. Here we're fitting some sort of parabolic thing, and here it's a I don't know, some higher degree thing. So the more we keep increasing D, the more the complexity increases. This becomes the same as polynomial regression, where a very highly complex model can overfit by memorizing the noise. So again, this is also a trade-off to decide the optimal value of D. And both these values of C and D, they're decided by cross-validation. So that's polynomial kernel. Next is the radial basis kernel. For this, the kernel is the Gaussian thing. And the only thing that we can control in this is the standard deviation, sigma. Sigma controls the spread. This radial basis kernel, as the name suggests, it helps us get circular boundaries. So if you see this case, we have the yellow class and the red class. What we're getting is these blue decision boundaries. Sorry, which is basically, yeah, circle. So smaller standard deviation leads to tighter clusters, and large standard deviation leads to smoother clusters. But this can overfit. So this can underfit. Smaller sigma can overfit. So that's kernel SVM. Now, if anyone has any doubt, otherwise, Anway, you can go with the code. Anway, you can present it.
All right, sure.
Yeah.
Yeah, okay. So this is the code implementation for SVM. We'll start with hard margin SVM first. I've imported the modules. In sklearn, you have an SVM module itself, which does everything. I've made this data set where I've distinctly made the data linearly separable. There's a long gap in between, and it's linearly separable. So for linear SVMs in sklearn, we can, as Vedant said, if you have a very high C, the margin becomes stricter. So this is what I've done. I put a very high C here, 10 to the power 10. And if your kernel is linear, it's defined here. And when you fit this model, you extract your coefficients. And so the plane you get is W0 X1, X0 X1 plus W0 W2 X2, W1 X2. And based on that, W0 is your X and your W1 is your Y. So your X2 is your Y and your X1 is your X. And based on that, we can just plot. So I've just done this for the sake of plotting. And yeah, this is the decision boundary our SVM makes for this data set. Similarly, now let's go to soft margin SVMs. In soft margin SVMs, again, we make a data set. Here I've made the data set less linearly separable, as you can see here. And again, kernel, and we put a smaller C value here to approximate a softer margin. Same set of processes here to get the hyperplane. And yes, this is our plot. Okay. Then we go to polynomial kernel SVM. Here, I've used the make moons thing from sklearn or datasets. Make moons basically makes a moon-shaped data set here. You can choose your different parameters, numbers, samples, and random state to define the type of moons you want. And this line here converts. So basically, the dataset sklearn makes make moons, and it defines class 0 and class 1. I have just converted the classes to -1 and 1 for the sake of SVM calculation. By the way, your sklearn module does this on your own, but I've just done this for the sake of calculations. Yeah, SVM.svc. Then we call the kernel polynomial here. You can choose a degree. You can choose your C. You fit your value, and then this is just plotting code. And you can see this is the decision boundary we got. We can play around with the C's to see if we can somehow incorporate this, or we can change the degree to see if somehow our decision boundary can include this. But for these set of parameters, this was the best decision boundary. Yeah. And radial basis kernel SVM, it's the same thing here. To generate data set, I've used the sklearn. The data says make circles. It makes two circles. You can choose the factor here is the radius ratio, noise is the noise, number of samples, how many data points you want. And I've done the same thing here. It classifies it as 0 and 1. I've made it -1 and 1 for the sake of SVM calculations. And yeah, you call the kernel RBF here in the module. You define a C, you fit the model, and this is again plotting code. So this is, you can see that the decision boundary has captured our data set. Yeah, that's all for SVM code implementation. Are there any doubts? Okay. If not, then I'll start with the next topic, which is naive Bayes. I'll just share my screen. Just a second. Yeah. Okay. Yeah, so we'll start naive Bayes classifiers. This is a very simple topic, and it is based on the probability formula we all have learned in JEE as well. So this shouldn't be something hard. So there are the two most popular naive Bayes algorithms are multinomial naive Bayes, which is used for discrete data, and Gaussian naive Bayes, which is used for continuous data. So this is based on the popular Bayes theorem, which is P of probability of event A happening given B has happened is equal to the probability of B given A has happened times the probability of A by the probability of B. This is the standard formula we've learned in JEE, and this is the formula which is going to be applied everywhere in naive Bayes algorithms. Okay. So yeah, let's start with multinomial naive Bayes. Multinomial naive Bayes is only used is when the features of the dataset are discrete. It is used for tasks like spam, not spam, any classification tasks. Okay, thanks, Vedant. Just a second.
Oh, wait, sorry. The graph changed.
Yeah, that's fine. Yeah. Where's that? Okay, so it is used for classification of text data. You can, like, if you want to classify if something is spam, not spam, or if it's like positive or negative feedback and so on. So let's start with an example, a very simple example. Here I have made this data set where not spam has these four messages in it: hi friend, dear, friend, lunch, give money. And spam has these text values: money, money, friend, and dear, take money. Now let's given a new sentence, dear friend, we will use multinomial naive Bayes to figure out whether this data is spam or not spam. Now, how do we do this? We try to compute two probabilities, which is probability that this is spam, probability that it's spam given the test set, so probability that it's spam given dear friend, or probability that it's not spam given dear friend. So again, the way we calculate this is via that Bayes theorem formula, which is this. This is going to be used everywhere, as I said. So yeah, let's go on. So algorithm, how we start is we first find the probability of the class. So which is P of spam is 2/6 because we only have 2 spam sentences in our data set out of total 6 sentences. And we have 4/6 is for not spam. Then we try to find the probability of the word given that class. And then we try to find the probability of the class given that test set. So if we have to find P of spam given dear set using using the Bayes theorem, it will be probability of dear friend given spam times probability of spam divided by probability of dear friend. Similarly, this will be that probability of dear friend given not spam times probability of not spam divided by probability of dear friend. Now, I choose to omit probability of dear friend in both the denominators because it doesn't matter. It's the same denominator for both. So if in the end, when we're computing the probabilities and comparing them, it doesn't matter. It's just a constant. So we can just, for the sake of simplicity and for the sake of calculations, we just assume it to be 1 in all cases. As it does, and it won't affect the scores in comparison. So yeah, then let's calculate for this. P of spam given dear friend will be probability of dear friend given spam times the probability of spam. So this is equal to the probability of dear given spam times the probability of friend given spam times the probability of spam. So if we go to our data set again, probability of dear given spam is 1/7. Probability of a friend given spam is 1/7, and probability of spam is 2/6. So we get this probability. Similarly, the probability of this via the data set is this. Now, can anyone tell me, like, what's the issue with this? There's something we're assuming here. Can anyone, like, tell me what exactly are we assuming in this case, in these calculations? There's one big assumption we're making here, and I'll talk about the
Assuming
reason.
everything is independent.
Right? Yeah, exactly. So this is why it's naive. Why do we call it naive? Because naive Bayes in its algorithm assumes that the probability of dear given spam times and the probability of friend given spam is completely independent. It doesn't matter how many times dear comes in my data set, that will not affect the probability of friend coming in my data set, which is obviously wrong, right? Because because that means that having the word dear will give me no clue about whether my data set contains friend. That is the biggest assumption we make in naive Bayes. And like you can say, I mean, it's true, right? It's a very like weird assumption you can say, because in real spam data sets, a lot of words can co-occur, right? If we have one word, we can the other a possibility of other words can occur. For example, if my spam data set has the word give, then we can say in some sense that the word money should be present in a data set, because give money could be something in a spam data set, right? And another reason why it's naive is because it has no idea about your sequence of words. The sentence dear friend I ate your lunch and friend dear lunch I your ate, they both have the same exact words, but this looks like it's not spam, this looks like it's something spammy, right? But in multinomial naive Bayes, these both will get the same probability score. So that is one more drawback of this, and that's one more reason why it's called naive, because of these two assumptions and the way it works. Yeah. So, and one more issue now. Let's see. So if I want to see if this sentence is spam or not spam, lunch, 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 money. If we go to our data set here, we don't have the word lunch here. So automatically, when we try to find the probability of lunch given spam, is going to be 0, right? So automatically, when we calculate our probabilities, this sentence is going to have 0 probability for spam, and it's going to have 1 probability for not spam. So obviously that's wrong, right? This is something which is very spammy. So how do we solve this issue, right? If something exists in one data set and doesn't, but it could hugely misclassify your sentences. So we use something called Laplace smoothing for that, where what we do is, if any word exists in either of the classes, we assume it exists in the overall vocabulary. So lunch here existed in the data set not spam. So what we do is we assume that the word lunch also exists in spam by adding a count of 1 to the overall data set. So if I have the word lunch in not spam, but it's not there in spam, then what I do is I add +1 to all the word counts together. So now the word count of lunch in spam becomes 1, and the word count of lunch in not spam would become 2. So I mean, you can choose any arbitrary constant to add, and we choose 1 for easier probability calculations as well. So this is what Laplace smoothing does. It makes sure that everything is included in the vocabulary to prevent such misclassifications from happening. So yeah, so then your probability would change that frequency of that word +1 divided by n class plus v, which is your total vocabulary size, because you're adding 1 to each vocabulary word, each word in the vocabulary. So your total denominator would get added by a plus v. So yeah, this is Laplace smoothing, and yeah, okay. Then let's, any doubts still here, by the way, before I continue? Anything in the calculations or the way this whole thing works? Okay, so then I'll go to Gaussian naive Bayes. So, okay, so multinomial naive Bayes was used for discrete data, right? We had a word data set here. Everything was tokenized. We had token counts, and we had probabilities via counting. Now, Gaussian naive Bayes is used when your data set, when you want the features of your data set to have some continuity, and it's based on this Gaussian distribution curve, this Gaussian bell curve, via this formula. This f of x, if you plug in values of x, you'll get this curve. It's dependent on your mean and your variance. Yeah. So let's take an example. Say this is from a very popular YouTube video, if you guys can see. So say you have the quantity of popcorn, soda, and candy bought during a movie show called Troll 2. We need to see, okay, if we have this much quantity bought, then does the person love Troll 2 or does the person not love Troll 2? That's our goal here. We need to see whether given quantity, does the person like the movie or dislike the movie. Now, we have this training set. If we're given a new value for P, S, and C, does the person like the movie or dislike the movie? That's what we're going to figure out using Gaussian naive Bayes. Yeah. So what we do is, if you're given a new value, we assume to figure out the probabilities, we assume that these features follow a Gaussian distribution. So if I want to find the probability of, say, probability of popcorn given they like Troll 2, then I would use this formula here, where y is your class and x is your feature. So this is x minus the mean of that instance in your class. So the mean of, say, if I want to find it for popcorn, then this mu is the mean of this column, of all the values in this column. And your sigma squared is the sigma squared for all the values in this column. So that's how we compute the probability. We assume our data set follows a Gaussian distribution. So the probability of popcorn follows a Gaussian distribution. Everything just follows a Gaussian distribution here. Right. Then to predict that the person likes Troll 2 is the same naive Bayes algorithm. It's the same Bayes theorem algorithm, where it is P of A by A bar B is equal to P of B bar A times P of A by P of B. We use the same algorithm here, but when if you guys recall clearly, for multinomial naive Bayes, if we had to find, say, P of deer time given spam, we had done counting. In the same case, now if you want to find P of popcorn given likes Troll 2, we will just plug it into this formula. That's the only difference here, is we assume that they all follow a Gaussian distribution. So let's just try to compute it together. if the probability that a person likes troll 2 given the values of popcorn, candy, and soda is equal to the probability, using this is the base theorem, probability that the person likes troll 2 times the probability that the person likes popcorn given they like troll 2 times the probability that the person likes candy given that they like troll 2 times the probability that they like soda given that they like troll 2. That's the same formula. And here we find these using the Gaussian formula. Here, the probability of likes troll 2 is half because they either like the movie or dislike the movie for our case. And you compute the same thing for doesn't like troll 2 using the same way. Yeah. Now, before I move on, can someone also tell me what could be an issue with this? Like, I'm using the Gaussian distribution to figure out these three probabilities. What can be like one drawback of this method of calculation? Here's the Gaussian formula and everything. Like it could be a drawback in terms of calculations, if you could think in that way. All right, so I'll just tell it then. See, what happens is when we try to find the probability of, say, the person of some popcorn value here, it's very, very close to zero. Similarly, if you want to find the probability of candy value, say here, it's very, very, very close to zero. So when you do all of these multiplications to find this probability, you're multiplying something very close to zero times very close to zero times very close to zero for some case. And in computers, when you multiply something extremely close to zero, tending to zero multiple times due to something called underflow in computers, these computers approximate them to be zero. They approximate these small multiplications to be zero. And that can be an issue because that's not representing our probabilities exactly, right? Because this may be something non-zero. So what we do is, to fix this issue, we take the log on both sides. In this formula, we just take the log on both sides. So the log of probability of this equals to the log of this, the log of probability of this, plus log of this, plus log of this, plus log of this, plus log of this. So this fixes our issue of, even if we have very small values of probability, the log will make sure that it doesn't happen and our multiplications can take place normally. So we just take the log of this on both sides, and then again, whichever has the highest value, it belongs to that class. Yeah, that's Gaussian naive Bayes. If there's anyone have any doubts here?
Won't the log give a negative value for these probabilities because they have in 0 to 1?
Right. Yeah. So there we choose the magnitude. Whichever has a higher magnitude, it belongs to that class.
Yeah, got it.
Right. Yeah. Cool. Then I will take the code implementation. Yeah. So let's start with multinomial naive Bayes. For multinomial naive Bayes, I've used this 20 news groups data set where you have a lot of posts and they're classified into multiple categories like basketball, which is in sports category, football, space and science category, and so on. So each post made in this news group data set has been classified and labeled properly. I've also attached a documentation because we're importing it from scikit-learn. You guys can explore that. And yeah, so we import this data set. We import count vectorizer. This is to take a count. So in multinomial naive Bayes, we make it tokens and then we count the tokens, right? So this is what count vectorizer does. I'll talk about it in detail later on. Naive Bayes, chain test split, and then confusion matrix. So we load the data. For this case, I'm just for the sake of simplicity, I've just imported two, which is space and hockey data. And we're just cleaning the data here. So we have the text and we have the labels. Now we use count vectorizer. What count vectorizer does is, it first, say we have a sentence like Vedant is playing basketball, Vedant fell down a tree, something like that. It will take all the unique words, which is Vedant is playing basketball, fell down a tree. These are the unique words in the vocabulary. It first creates a vocabulary with all the unique words in it. Then for each sentence, it forms a vector. So now once your vocabulary is made, so it goes through all of the sentences in your data set and it finds all the unique words. Then it makes a vocabulary. Now after that, it's like a list where you could say, or an array, where it reads every sentence and it adds a count to your array under each word. So as it reads sentences, for each sentence, there will be a unique vector which will tell it the count of each word from that vocabulary that occurs in that sentence. Then you just concatenate, it returns a matrix of token counts. It just concatenates all vectors together for all the sentences in the training data. And then we feed that into multinomial naive Bayes because that gives it the count. So we've done that here. We vectorize the text and we fit it here. It gives us the count. We do train test split as usual for figuring out the accuracy, and we predict. So we fit it to the model. And here are some example predictions. So you can see our model has done pretty well actually. It almost classifies everything right. There is one case here where I believe it doesn't do it well, right? Yeah, here. So did it roll out already? I'm going to have more. Yeah. So I mean, okay, you can't really blame the model here. It looks a little blurry, but yeah. And then this is the confusion matrix, the classification report. Yeah. So that is multinomial naive Bayes. Then let's go into Gaussian naive Bayes. Gaussian naive Bayes, here I've used the iris dataset. And we're going to use, since the iris dataset has a lot of numerical values and we'll assume it to have a Gaussian distribution. That's one assumption of Gaussian naive Bayes. It assumes your data has a Gaussian distribution. We load the data set, we do train test split and all. Yeah. So we load the data set, we're performing train test split, and then we just fit it to your Gaussian naive Bayes model. It does all the Gaussian algorithms the same way, and we make predictions. Now, this is the accuracy. We gave it new data here, by the way. I've given it new features, new data for these features, and it's giving a prediction. So yes, so it has three targets, 0, 1, 2. So the model predicts that this class belongs to Setosa, and this class belongs to versicolor. Yes, that's the code implementation of Gaussian naive Bayes. It's pretty simple. Any doubts here?
Yeah, even if you guys have any doubts regarding the previous topics, of you guys can ask right now.